So last time we did a one-dimensional elastic collision, and I want to point out one result of that one-dimensional elastic collision. This was a special case where the two masses, we ended up just make the math easy. We made the two masses the same, and we had one of them had an initial velocity of 0. But what I do want to point out is something of a more general result. Notice that initially Jack's velocity was 3 meters per second east, and Jill's velocity, east was plus x direction. Jill's velocity was 0. What is their relative velocity? What is the concept of relative velocity? Let me come back to that one and just say, let's just take two cars that are going at some arbitrary velocities. I have car 1 going east at 10 meters per second and car 2 going east at 14 meters per second. How fast do they go relative to each other? Right, relative to each other, car 2 is going 4 meters per second faster than car 1. So we say their relative velocity, v relative, is equal to v2 minus v1. It could also be v1 minus v2. It doesn't matter. It's their relative velocity. It's one relative to the other. Well, I guess actually, according to car 1, right, he says car 1, the person in car 1 says, oh, car 2 is going at velocity v2, but I'm going at velocity v1, so I have to subtract my velocity from car 2 to say what my relative velocity is relative to car 2. And car 1 will say, my relative velocity is 4 meters per second. I'm sorry, car 1 will say car 2's relative velocity, car 2 is going 14 meters per second relative to the road, but relative to me, car 2 is going at 4 meters per second, 4 meters per second faster than me. Car 2, on the other hand, v relative would say it's v1 minus v2, according to 2. So the magnitude of the relative velocity is the same for each car, right? Each car sees the same relative velocity. Car 1 sees car 2 is going away at 4 meters per second. Car 2 sees car 1 going away at 4 meters per second. So I want to think about that relative velocity. Oh, and it's the same for each frame of reference, or for each observer, for each car. That's the right terminology. So let's just look at this for the roller coaster, for the bumper car example. I want you to notice that that initially Jack was going 3 meters per second east and then had an elastic collision with Jill, and then Jill was going 3 meters per second east. So what is the relative speed, the relative velocity, or the magnitude of the relative velocity before the collision? Jack is going 3 meters per second east, and Jill is sitting still. So Jill says their relative velocity is Jack is moving at 3 meters per second towards her, 3 meters per second east. After the collision, Jill is moving at 3 meters per second east, and Jack is sitting still. So Jack is actually moving relative to Jill at 3 meters per second west. So it is important to recognize that their relative velocities, according to Jill, have reversed, but that they have the same magnitude is what's important. Is the magnitude of the relative velocity is still the same. And this is actually the hallmark of an elastic collision. In an elastic collision, even not for the special case of same masses, not for the special case of one where one is sitting still at some point, that actually in every elastic collision, if you take the momentum in general and the energy in general for different velocities and different masses, and you solve them together, what you always find is that the relative velocity before the collision is equal in magnitude to the relative velocity after the collision. So that is actually a useful fact that helps us at least check our answers, if not helps us get to an answer, that their relative velocities are the same. Now, it does reverse in direction, right? So the relative velocity before the collision, according to one observer, is equal to the negative of the relative velocity after the collision, according to that one observer. Again, looking at this example where, according to Jill, Jack was going 3 meters per second east before the collision, and according to Jill, Jack is now going away from her, going 3 meters per second west, because Jill's the one moving east after the collision. Or according to Jack, initially, Jill is coming at him. So Jill is coming at him at 3 meters per second west. After the collision, Jill is going away from him at 3 meters per second east. So, but this is important to understand, and we haven't proven it, but it is true, that the relative velocity before the collision is equal in magnitude to the relative velocity after the collision for either observer. And for one observer, the direction is the negative, right? They're coming towards and they're going away. And this comes from a solution that we didn't do because it's really messy algebra of solving these two equations together in general. Equation form, this is what we just said. Doesn't matter who 2 and 1 is, you can switch their places and this is still true for any elastic collision in 2 dimensions, in 3 dimensions, etc. Okay.